I'm here to talk about the data collection architecture that we are using on the ICE laboratory, and we are developing at UniVR. This data collection is based on Kubernetes and relies on OPC-UA as communication protocol, but not only OPC-UA, as you will see in a few slides. This presentation is divided in some parts: a brief introduction followed by a background concept to understand correctly the topics. Then I'll move to the description of the architecture, firstly with a high level of detail. So I describe which nodes are active and their communication. Then I'll give some details about the node configuration, so to get to be more technical. Then I move to the requirements, so how the architecture can be installed, and since there are a few methods, and then I'll explain exactly what we are doing at the ICE laboratory, so providing also some screenshots about the system.
By the way, Marco, before following on, let me also say that all the slides are on the Moodle page, okay? Your slide and also the slides of the workshop of next Monday about embedded AI and AI and embedded architecture. Okay, thank you. Go on.
Thank you. So for the introduction, our prerequisite is to get a plant. So we are an industry, and we need to monitor, collect our plant and the state of our machines. So the architecture requires that each machine and eventually some other sensors like IoT or industrial IoT expose the information using the OPC-UA protocol. So this is the first step that a company has to meet. The goal of the architecture is clear, so it is monitoring, logging, and clearly giving the possibility to analyze online and offline all the data collected. The solution is the architecture. Clearly, the architecture goals are, as I already said, the monitoring, the possibility to log all the information and to persist and store them locally, and if the company wants to do that, move some part of data to a public cloud, for example, Amazon, IBM, and so on. Another feature is the architecture provides a unique interface. So when the data is stored on the database, there is a unique layer with a unique API that an external user can use to read, write, and perform analysis on the data. Clearly, all the features are put aside the security, so the security must be guaranteed. So we guarantee encrypted communication and the possibility to authenticate users, to give also different privileges. Some background concept to understand the system. The first is the concept of container. Maybe you already know something, but the container, as taking the exact definition, says that a container is an abstraction that packages code and dependencies together. So it is a file, an entity that contains the applications of the executable, compiled, or script, if depending on the programming language, and all the external libraries that the application requires to work correctly. Some keywords that are common to this word: the concept of container image. So when we create a container image, we take exactly the application, the libraries, and we compose them together using a recipe, following the steps of a recipe, which is called Dockerfile. When then we execute a container image, we get the exactly named container. So these entities can be compared to the object-oriented paradigm as a class and instance. So we could have a container image a single container image that can be executed many times, and each instance of the image is called a container. Another concept is the container registry, which is a server that has to store all the container images written by the user or others, and make them available to other systems. And well, maybe the name, maybe you have maybe already known the name, but commonly used, the most commonly used container engine that in these days is Docker. A few examples of history for starting with the IT world. First, years ago, in a company, there were many servers, each with its own operating system, and over each server there were different applications. In this example, clearly there is one application per server, but it is an extremization to get to explain better the things. In this situation, we have, for example, 3 physical servers, 3 instances of the operating system, and 3 applications. Then, with the advent of virtual machines, we reduce the physical number of servers using clearly machine with more resources, for example, RAM and number of CPU. Over the single server, like always for this example, we instantiate an hypervisor, and over the hypervisor we can instantiate different virtual machines, each with its operating system, then libraries, and finally the application. This is a better solution, but there is a problem since the operating system guessed, clearly, because this isn't the operating system of the physical machine, but it is related to the virtual machine. It is executed more than one time, so there is some overhead. The container solution resolves this problem by moving the operating system down in this graph, in this image, and we have now one single server, clearly same always for this example, with one operating system that is executed. Over the operating system, there is a container engine which uses API or features that are already available in the kernel, but expose them with an interface with a more usable interface. And over the container engine, we can instantiate our application. So this is the better solution with less overhead due to single operating system, and also the overhead of using a container instead of a native application is very limited. Clearly, the use of container can also have some drawback. For example, in a real context, it is common to have a very large number of containers running on a single machine or a multiple machine. So it is very complex to monitor and check the functionalities of the performance of the overall system. The solution is to adopt a container orchestration tool, and the most common, the most important, the most developed is Kubernetes, which is maintained from CNCF Foundation. Kubernetes works over a cluster of machines. Each machine has a role. There is, for example, the master node. In this example, we have in a real system, probably there will be more than master to provide high availability. And the master communicates with different worker nodes, which are the nodes in which we will deploy our application. The master node is responsible to keep track of the nodes, their availability, their status, and it is the master which deploys the containers to the different workers. Clearly, the worker and the master are connected each other with the physical Ethernet networks, but it is possible to build different routing or network mechanism virtual, so using particular interfaces. Another function of the master node is to expose, first of all, the Kubernetes API, which allows an external client to interact with Kubernetes and, for example, deploy application or check their status. Another thing important is to the ingress concept, which in particular has the role to route the request from an external client, so I use a PC or a smartphone, to the correct container. This is necessary since the user does not know in which worker node a single application will be run, because it is the master which handles this thing, and so this is necessary that the master be able to route requests to the correct application. Another thing that the master do is the handling of the automatic replication. So in this example, we have application one, the container with application one, which is executed on different nodes, and these are called replicas. This is necessary, for example, when the load or the resources that application need to use are not available on a single node, and so the Kubernetes can decide to deploy, to start other application instances, and clearly then the master will route the large number of requests from the external to the different instances with different policies. This operation can be configured, so it is possible to decide to instruct Kubernetes to when it is necessary to scale up an application, and when otherwise it is possible to stop some instances to always provide higher performance and higher availability of our application. Let's move now to the architecture. So with a description of the architecture, as I already said, all the nodes of our architecture are running to containers. This is clear because the architecture is built over Kubernetes, and this is a requirement to load an application. Another common thing of the container world, or the container way of work, is to make the container image configurable with the environment variables. This is they are used as like a command line in Kubernetes in container world, because when we start a container, we cannot add parameter to that, but we can change the environment in which the application will run. So each node of the cluster is configured by environment variable, and when the node starts, reads them to perform the requested operation. So as said before, the architecture starts from a plant with IoT sensor or industrial IoT and equipments that expose their data with the OPC-way protocol. In this image, every circle can be seen as a single instance of an OPC-way server. I don't know if you are familiar with this protocol, but OPC-way uses puts servers on the machines and exposes a data model. So each machine is always listening for connections, and the client who connects can browse this data model of the machine, and inside this model there are variables, methods, objects. The client can browse, read, and write these objects, so can interact. The first node of the architecture is, in fact, OPC-way clients. So also here, every circle is an instance of a client. So we have different containers of the same container image, each one configured with different parameters. In this case, we can see that each client is bound to a single server. There is a case, if you see my arrow, I'm pointing that, in which a single server is, there are two clients connected to the same server. This is possible, and it is common. It is done when there are lots of data to extract from the server, and it is useful to split them into instances. The OPCO client so reads data from the machines or the IoT sensor and writes them immediately to a data buffer which uses the publish subscribe paradigm. The publish subscribe, it is also similar to paradigm is similar to the one used in the MQTT protocol. There is the concept of topic in which is a string, and there are two main entities, producers and consumers. In our case, the clients are pure producers, so each client produces, they write the data to a particular topic. For example, the topic could be the name of a machine to distinguish between the instances. All data is sent to the publish subscribe buffer, and this buffer acts as a broker, so it is work to repartition, rewrites all the information to the consumer. Each consumer is subscribed to one or more topics, so it receives also the topic of interest. In this image, we can see also that the data buffer has some replicas, 1 or n. That's because since this is a very heavy node, it is possible to add more instances of this node to guarantee the performance. The first node, when data are sent to the buffer, now they must be redirected to the database. So to act as a bridge from the data buffer and database, we have developed a data uploader node. Then it will be described more in detail in the last part of the slide, which subscribes to a topic group and reconverts the data and uses the database API to write them to the DB. Clearly, we use the concept of topic group because we can take the old topics, partition them, and deploy more than one instance of the data uploader. Always in the context of keeping the performance high and to not lose values. Finally, in the database, so the data uploader writes the data to the database. Also, the database can be replicated, so same concept. And clearly, the database must write data to a persistent volume. Persistent volume is a Kubernetes term which can be compared to the volume of a Docker container. That means simply that this container instance can write data on a portion of a drive, and it is guaranteed that data cannot be lost in case of container crash or restart. When data are on the we use a time series database, not a NoSQL one, not a SQL one, because the data we get from the machines are not always uses the same schema. So it should be difficult to define a SQL schema that fits always all the data we get. Clearly, we are working to start a SQL database that will be put on the side of this one, and they will work together to store the data in the best database that can get them. Okay, when the data are on the time series database, I forgot, we have also a Syslog server instance. So each application writes its log to and expose them using the Syslog protocol. So and we have an instance that gets them and converts them, writing the data to a database, so always to the same database. Clearly in a dedicated area, so we can analyze also only Syslog and only the data from the machines. As said before, when data on the database, we give the possibility to choose a part of them and write to an external cloud, which could be public or private of the company. So we developed a data selector node and a cloud uploader. So the data selector simply queries the database, clearly the query or the filter that will be applied can be chosen by the user, and extract only a part of the data, passing then to the cloud uploader that will use the cloud, in this case, the Cloud A API to write the data. The choice to use or not this possibility depends usually from company policies, since not all the companies are happy to send their information to an external cloud, but we provide this possibility in case it is a requirement. We have then developed different applications that queries data directly from the database, and you will see at the end of this slide, for example, Iot Data Viewer and Industrial IoT Data Viewer, and clearly it is the possibility to extend this to develop other system and connect them with the database. It is also possible to choose other cloud providers and write the correct agent that can communicate with the cloud. As you can see, each cloud has its own API, and so there is it is only necessary to get the correct library and write a simple application. Another pro of the publish subscribe paradigm is the possibility to add in other clients. So if we add, for example, another machine or extra data sources of another type, of another kind, without altering the rest of the system, the only requirement is that we should always use new topics to don't interfere with the rest of the communication. Always the publish subscribe paradigm allows us to split, to send the data from the Opcway client to more than one node, so clearly from the data uploader, but also to, for example, a safety monitor, so a node that monitors that the plant is working correctly as defined, and in case this is not happening, it can, I don't know, send an alarm, or in the future act with feedback to set some parameter directly to the machines. Now I'll explain single node more in detail. Start with the Opcway client. Clearly, as I said, is the data ingress node, so it is the first node in which the data from the external arrives. It is configurable, so for example, we will see then more in detail, but for example, we can set clearly the server to which it has to connect, and then the list of variables to monitor. For each variable, we can provide the sampling interval, the data type and unit that we want to use when storing data, and we give the possibility to add static fields. So if the user has to add some information, some extra information to that value, it is possible to do that. We have and I have also an example of this. The last argument is the topic name to publish. So the client must, when send data to the broker, must send them to a topic. So this must be provided. Then these nodes are optimized to move more data as possible, and clearly the requirement is to get at least one instance per machine to get all the data. After the Opcway client, we have the data buffer. As already said, it is a broker with the publish subscribe. It has the possibility to scale to guarantee fault tolerance and high performance. So we will have a single instance per physical machine. So in case of crash of a single host, the system shouldn't lose any information. And as said, the publish subscribe allows us to add extra producer or consumer without edit or stop maybe the rest of the system. The data uploader node, also here, it has the role to transfer data from the broker to the database. So it's subscribed to a topic group, so not to a single topic, but to a group. This is allowed to be scalable. And also the uses send frequency lower than the one used by the OPC, from the OPC clients. So that means that this node will not excessively send data to the database, single data. So you prefer to send chunk at period with more large to reduce the computation from the database. Finally, the database, it is a NoSQL one, in particular an time. So a database specialized to store time series that are series of data with values, and each value has always a timestamp associated. It is the only node in our system that stores data in a persistent volume. So what it writes is stored in a persistent way, and clearly has the possibility with queries to filter the incoming values and perform further analysis in the second moment. The common way to store data in this kind of database is to use buckets. And buckets are used to partition all the data of the database to logically partition the data. In our example, we are using 3 buckets, raw, client to cloud. The name are auto-explicative maybe. So in the raw bucket, we store all the data we receive from the field. We want to do that also to give us the possibility to apply machine learning algorithms in a second moment to collect the data. Clean stores the information which have been filtered or pre-processed from the raw bucket. So the clean is probably the correct bucket to use when a user wants to read or to monitor the system. And finally, the to cloud, which is the bucket in which are stored the values that the agent will be sent to the cloud. Also here, there are different instances that managed by the Kubernetes system. Another node that is available and I haven't described is the data analyzers. They are ready for the user, so the skeleton is already developed, and they allow to apply an algorithm of every kind. So it is up to the user to decide what he wants to do, and to the data of the database. So these nodes can be deployed, and they read and write data to the database. We use one of them, for example, to transfer data from the raw bucket to the clean bucket. And finally, the cloud uploader, as said in the big scheme, for each cloud we need to develop an agent and a data set, and one or more data selector. The data selector moves data eventually. Clearly not only moves, but it can aggregate them, remove some junk values and so on, and writes only the values that we want to send to the cloud to the dedicated bucket, and the agent will execute the query from that bucket, transferring the values to the cloud, to its cloud. In this image, we have only one agent, but as written in this slide, since the agent executes a query to the database, it is possible that also the agent execute other pre-processing of the values and so on. Here we have an image describing what I already said. So we have the data upload that send data to the row. For example, we have an instance of the analyzer that filter the values, maybe removing some noise and write them to the clean data. Then the data selector of the cloud A writes another portion of data to the cloud A, and finally the agent do the final jump to the cloud A. Okay, requirements of this architecture. With requirements, I mean the possibility, different method of deploy of this entire system. We see three different ways with pros and cons. Clearly, the on-premise cluster Kubernetes, it is the more flexible solution. So we have the server in house or into the company, so we have full control of the performance of the hardware and also the software. Another pro it is that all the data we collect is stored inside the company, except for the one sent to the cloud exactly. And this for industry, it is often a very important requirement. And clearly, the performance of the entire system depends on the node. In fact, if we don't have enough processing power, clearly the system will be slow. The cons of this system is the initial cost of the hardware, clearly. The possible cost of software licenses, in this case, depends of the target of the installation. For example, if the installation needs to be certified, or we are in a context in which an open source license with clearly the possibility of have crash or similar, it is admissible. So it depends if a licensed version of Kubernetes is requested because we are in a critical environment. The cost of the software is very, very important. And clearly, since we have a server in the company, we need the staff that follow the system and manage them. The second option is the use of the cluster Kubernetes on cloud. Here, we have the opposite. So as far as we pay, we have enough performance is a storage, but clearly it is all stored and executed outside, so in the cloud, and maybe we doesn't know also the country. So the primary cons is the cost of the cloud service and the fact that the data are stored outside the company. But in this case, there is also another problem, that is the internet connection of the plant. So it is necessary to expose the machines of the plant directly to an external system, and this could be risky, except when using VPN. But also in this case, the performances could be less than could be not bad. The third option, which I reported for completion, but is not, I will not use that. It is the skip of the container and use the single application as node on virtual machine or physical server. So also in this case, we have the pros of the full control of the system, but it will be very difficult to do the first installation, because when with a container we only need to start it, but when we not use a container, there is also a problem related to the setup of the libraries, the setup of the operating system, the version of the operating system, and so on. Also, since we are not using containers and So Kubernetes, we don't have high availability and fault tolerance. We could implement some custom logic, but all this stuff could be local and not maintained. So clearly the preferred installation is one of the first of the second, depending of the company policy. Let's now move to the case of the application of this system to the ICE laboratory. Here I have some screenshots of the lab. I think that all of you knows or at least all the history of the lab and its goals. So we have we can see here the different machines. Some are already here. Other will arrive soon. And the important thing that in each of the machines you see here provide an OPC web server. Some of them were already compatible with the protocol from the beginning. For others, we need to develop an OPC web server custom that interacts with the machine using its proprietary protocol. For example, I don't have a photo, but the vertical storage system doesn't provide an OPC web server natively, but since there is a Windows PC on the side, we developed an OPC web server that interacts with the storage system software and exposes the function and the data we need. Another important point of the ICE laboratory is the multiplicity of IoT sensors we have in this room, and all of them are collected by two Box.io gateways that we have in the rooms. We monitor temperature, humidity, brightness of each room, and in the next month we will monitor also the energy consumption of each ICE machine. So we will have information about the energy consumption of each robot, each conveyor of the lab, and we will correlate this information with the running recipe. Another thing in this image is a brief screenshot of the light control system we have in the lab, and this system is installed on a board inside a quadro elettrico. Sorry, I don't know the exact term. And we developed a custom driver that allowed the Box.io to communicate also with this board to read and also act on the lights. So starting from the actor, from the ICE lab, we have the two Box.io keeping IoT and industrial IoT data, and then the different OPC web servers of the machines. The OPC clients are Python applications. For the broker, for the public subscribed data buffer, we choose Apache Kafka. We also could use RabbitMQ, but we saw that they are similar both for performances and also for hardware software requirements. The data uploader has been split in the two different applications. We used we wrote a custom application. The current name is InfluxDB custom uploader, as you see in the next slide. But we also saw that with the Telegraph agent, which is an application that supports the transfer of data from a multitude of applications, it works well. So we have two options, and we can choose in base of our requirements of our requirements what kind of the tool to use. And as I said before, for the time series database, we choose the InfluxDB. The choice, for this choice, we do a brief research, and we saw that Influx is one of the most performant NoSQL databases when writing lots of data. So this is the reason of InfluxDB instead of, for example, MongoDB or some others. We now support only one external cloud, which is MindSphere, the solution of Siemens, for which we have an educational account, so we can use it at a small cost. And to transfer the data from the database to MindSphere, a Java application has been developed named iStorm, so ice to MindSphere, the name is clear, that simply transfer the information, providing the current mapping from the two sides. Then we also have the Iot Data Viewer and Industrial IoT Data Viewer, which are external applications written using the unique HMI software of ASM. So they are not up to now, they are not executed inside the cluster, but we are reasoning about this possibility, and we will do that in the next weeks or months, depending of the other thing to do. Some technical detail, we use this data format when transferring data from the OPCUA client to the InfluxDB. This format is in part taken, but the data structure that InfluxDB uses, but we saw that is almost extensible, so we used it. So the first keyword is the measurement, which is the first entity we saw in database. We associate this tag the machine. So for example, all the measurements that come from the vertical storage system will have a vertical storage system as value. Then we could have an optional list of tags. A tag will be stored as a column, in particular a column of the database, in which the name of the tag is the name of the column and the value clearly is the value. We can clearly use more than one tag. Then we have the timestamp in the format, one of the possible format. The interesting thing that we are using, we write also the decimal part of the timestamp, which is in seconds, and this value can reach also the nanosecond precision. So because InfluxDB support this precision. And finally, the field part, which is the core that contains exactly the variable and the value, for example, temperature and its value. Then we will see some example. This is one format, but always InfluxDB allows a second one, which is a protocol which uses, and it is also enough used, which is named the line protocol. This is a single line that represents the same information of the previous slide, but in a more compact way. If you, for one of you interested, there is with this URL you get the explanation of this protocol and how to escape strings and so on. As said, the configuration of the node is done using the environment. So I'll show you briefly how to configure some nodes using which environment variables are important to the tree developed node. Starting from the Opcway clients, we have different variables. The first are related to the connection part, so the URI of the URI of the Opcway server to connect. In reality, there are also other variable near this one to specify the kind of encryption to use. So if the user want to do a plain connection, or if you want to apply some security policy, and clearly the possibility to specify username and password of the user. On the Kafka side, also here the URI of the broker, so where to find the broker, and the name of the topic to which send data. Then logging variables, so log when pushing and write using line protocol as configuration that allow to, as the name says, to get the application, to make the application more verbose, so to get see in the log each data sent effectively, or and the selection of the format to use. Since the line protocol or the JSON format are similar, but for extensibility, we saw that the JSON is often a good choice. But maybe less supported by the Telegraph agent. Other variables, so the machine name, so the measurement name that will be used. As said before, the OPC clients connect to a single machine, and so it is easy to write this variable. And the default publishing interval in milliseconds. This is a particularity of OPCUA, but in practice, this is the period in which we can receive all the values read from the server. So we could use an Eiger polling interval, but we could now in any case receive the chunk of data each this period. Clearly, this value is this is the default one, but it could be applied to each single variable. Finally, the online variable name, this is used to track the availability of the machines. So each client is configured to send a particular variable, which indicates if the client is connected or not. By analyzing in a second time the values of this variable, we can extract the information and know when the terminating machine is online and not. And finally, the most important, OPCUA variables, and I'll explain in this slide, which is in practical using a YAML format, and this is the variable in which we specify all the variable, the node that we want the client monitors. So we have a list specifying the node ID, which is the unique identifier of a variable in OPCUA. All the values inside a single node ID are optional. So, for example, for the node ID 2, we use all the default values. So we didn't specify nothing. For the node ID 1, for example, there is the complete definition. The first three values are always related to the OPCUA protocol. So the way of the method that the server should use to monitor this variable, the publishing interval, as said in the previous slide, and the queue size. So this is the maximum number of value we can receive in a publishing interval, so in a period. There is also another variable that I have not written effectively, but it is the sampling time, which is obviously important. Then we can specify name, data type, if missing are extracted from the OPCUA specification, and finally a cast function. This is useful to have in case we have servers that exposes numbers using strings. This could be a problem because all the string data is propagated to the database, and then when try to execute queries, clearly maybe mathematical operators doesn't work because the data is treated as a string. It is possible to correct this data type immediately at the OPCUA client level. and then so to propagate the current value to the next of the system. And then an optional list of the custom tags we want to add to this variable. These tags will be added to the tag in the big JSON. Okay, let's now pass to the second node, the Python uploader. Clearly, because the Kafka, we didn't develop Kafka, but we only deployed it to the infrastructure, while we clearly developed the Python uploader. The Python uploader, similar to the Opcway, requires the information of the InfluxDB instance to connect, clear the URL, the bucket and the organization to write the data. So the bucket, because the organization is an entity defined by instance by InfluxDB to separate different bucket groups. So in our case, we are using a single organization, and it should be enough. And clearly the token, which is necessary to prevent unauthorized clients to write data to the database. The token must be generated from the InfluxDB interface. Then the information to connect to Kafka, so the broker, the list of topics to subscribe, clearly not only one, but a group, and a feature called group ID. The group ID is a Kafka feature, and it is used when we want to partition the values from different instances. For example, if we have a topic named cell4, and we have a node that produces value to this topic, we clearly, to read the values, we clearly instantiate a subscriber node that subscribes to this topic. But we have also the possibility to instantiate two subscriber nodes, which shares the same group ID. With this method, Kafka automatically partitions the data to both nodes, and so this results in dividing the traffic of the values. So it is a feature that it is very useful in case of Kubernetes. So we could start different instances of the same Python uploader, and since they had the different instances have the same group ID, the Kafka automatically automatically divides the information to the different nodes. Also here are different logging configurations, and there is two ways of push the data to the database, synchronous and asynchronous. With the synchronous mode, we immediately write each single value to the InfluxDB, so it is the fastest solution, but clearly the most heavy to compute, since each value is translated as a single HTTP request, which has its body and so on. The second way is the asynchronous mode, in which we can specify a batch of values to send that will be sent on each flash interval and so on. This is clearly the slowest method if we talk about real time or kind of real time, but it is the way that reduces the load of the entire system. Then the data selector, it is a node very simple. So, and also here the information to talk with the InfluxDB, information about logging, and the period in which the node executes does it works. And then the two working mode. The user can specify a custom influx query, or the user can specify a source and destination bucket. I move, okay. In base of the variable described, in the first method, this node moves all the data from the source to the destination bucket. The query automatically compute is this one. This is the Flux language used by InfluxDB. In practice, it reads the data from the source in the last query period, so in our case, for example, in the last 5 minutes, and writes all this data to the destination bucket. Clearly, this is an option, but we must provide the possibility to filter, aggregate, and so on. And so it is possible that the user provides a custom query. So the query clearly must follow a template, because the movement of data from the source and the destination must be preserved, but it is possible to add the operation of data inside the query, so to act as some kind of analysis. Now, a few examples of data flow, and then I should finish. Let's start from the first part of the architecture. So a data starting from an IoT sensor, and the travel of the data since the database. So we have a ZigBee sensor, which has its own ZigBee IDs. I didn't want to be more detailed about the ZigBee protocol, but each node has its own MAC address and so on. So the node with its ID, which is clearly more complex, wants to send a new value of temperature, in this case 22.06 degrees, with a timestamp written in the format year, month, day, T, hour, minute, second, and the time zone. The value is transmitted through the ZigBee protocol to the gateway, and then exposed to the Opcway protocol inside a node. The subscription mechanism of the Opcway sends a notification to the client, which receives that the node ID, for example, the node identified by the integer 40,000 and so on, 698 of the namespace 1 has changed value and has this information. So data type unit are automatically extracted by the Opcway data model. The value is the same, the timestamp is the same, and then point name here is a tag that the user who configured this client added in the configuration set before. The client gets this payload, this value, and writes it to the correct topic. In this case, an example was office/temperature. This method of using topics is common to use the slash to partition, to get a hierarchical structure or a similar hierarchical structure. Clearly, the payload is similar, but it is formatted as seen in the previous slide, so with the measurement, tags, time, and fields. As seen before, the machine name is the Box.io, Box.io ICE, so the Box.io inside the ICE lab. Data type unit and point name are tags, time is the time, and field, the temperature now is the field, so it is the variable, the important variable that has its value. Apache Kafka so gets this payload and sends the same data to the consumer node, which is subscribed to the correct topic. The node converts the value and sends, using the InfluxDB API, to the bucket ICE data, which is the row 1 in particular, of the organization ICE laboratory, and the data is the same. So the JSON can be ingested also by InfluxDB in an identical way, in a similar way that the line protocol. Then the second part, in which we will have the data, the temperature data inside the ICE data bucket. So in this image, you see the InfluxDB interface, and maybe I show you after, but there is the list of buckets, the list of measurements. So Box.io ICE, as you can see, we have different machines, L4, L5, conveyor, and so on. And then when we choose one of the measurements, we will filter more and more the query to different parts. So in this case, we are reading Box.io ICE temperature, and we select the data that the values that has the LMHT3 Odino as endpoint name. And the result is this graph. Then we have the analyzer node, which converts the data and sends the clear to the clean bucket. We have a very good sensor, so in this case the difference is minimal. And finally, the node ISTOM that reads the data from the bucket to the MindSphere bucket and reports the same curve, translating, acting, let me say, by defining a translation before our format and the MindSphere one, which is a little bit complex. Other example of other rooms, so for example, the temperature of another co-working 1 and 2, which are the offices near the ice. While in this image you see the temperature for the Odino lab, which is always in the same building. Other examples of temperature of lab ice meeting room, always on MindSphere. So these are data we sent to an external cloud. And another option used in MindSphere that allows to show binary values, since in this case we are plotting the room's occupancy. Okay, in this image it is not clear to the room of each series, but it is clear that the variable sends from 0 to 1, which are mapping to false and true. And these are the values of the occupancy of the 3 co-workings. Then the example of the IoT Data Viewer. This is a unique application that connects to the InfluxDB instance and through different queries extracts all the data of that are collected from the 2 box IOs. So for the ice lab, for example, we have temperature, humidity, and brightness, double in reality because we have 2 sensors. It is also reported the status of the lights, and this one is read from the building automation board. And also binary values that detect the presence of CO and the occupancy of the room. This is clearly the map of all the rooms near the ice lab, so the 2 co-workings, the meeting room, the server room, and the Odino lab. Another viewer that we developed is the Industrial IoT Data Viewer. This application is in particular focused on the transport line and shows the KPI that the system collects from the conveyor, in particular the total counter of the pneumatic actuation. So this is a lifter that can be moved up or down to move a mini pallet inside a bay or to make it proceed in the main belt, in the longer belt. Then the actual status of the motor, so if the motors is on or off, and okay, and nothing else in reality. The 3D model, we will extend this viewer, adding the data from clearly other machines, so the 2 robots and so on. Maybe also the 3D model can be, it is not updated, so we need to improve this visualizer. Okay, with this I finish my presentation. So if you have any question or
okay.
Yes, I have a couple of questions. When you talked about the architecture, you said that the safety monitor is connected to the buffer, but the buffer is limited in size. Am I right?
Not exactly in reality, because I'm moving to the right slide. Kafka is defined as a large streaming platform. So it is written to allow very large streaming of data. So, for example, it is used if I don't remember well, by Netflix and similar companies. So Kafka, it is not the limit. And Kafka can handle very large streams, megabytes, maybe more. Clearly, its performances are related to the hardware. So if we have enough processing power, we can transfer a lot.
Okay, and regarding this, what kind of hardware is used for the Kubernetes on-premise clusters?
Okay, is your question related to the minimal requirements, or do you want to know
Both.
what we are using now?
Both.
Okay. Well, the minimum requirements is related in reality to the distribution of Kubernetes you want to deploy. Since let me say the first one is K8s, which is the most complete and heavy. But also this one is sent in different for different vendors. For example, OpenShift from Red Hat, or Rancher from Rancher Data, maybe the company, I don't remember. So they have different minimum requirements for the Kubernetes layer. Then clearly the rest of the system depends on the application you want to do and the number of replicas. In our case, we are waiting for the HPC of the computer science department to get ready to deploy all this system to that. In the HPC, we will have 3 or 4 worker nodes, each with 16 cores, and I don't remember if 32 or 64 gigabytes of RAM each. And there are also 3 master nodes, so not one. And each master, it is small, but not too much, because if I don't remember, there were 4 cores and 16 gigabytes of RAM per master. Actually, instead, we have deployed K3s, which is a lightweight version, in the server room of the ICE laboratory, and we are using now 3 PC of the Cyber Physical Lab. So they have a Core i5 quad core, maybe with hyperthreading, and 8 gigabytes of RAM per node. We did not yet run performance testing in reality. It is one of the next steps to find out the limit of the actual system, of the actual hardware. And we are working to set up some producer node at the OPC1 layer, clearly. And we want to increase the amount of data generated until we find the limit of our current hardware. I don't know if I...
Yes. And with respect to the amount of data generated, how much, what is the size of the data per day?
Well, actually, we did not yet monitor high frequency values, because we are, let me think about the correct word. We are, the OPCway protocol has some problems when we want to use very high pulse sampling frequency. So if we want to get values at maybe 100 values per second, we are also doing some tests to evaluate this one. And if this is possible, okay, we will use the system, but we are not ready in this part. We have also developing other nodes that will be put inside of the UPC-way that support other protocols, and we will want to use them to in the cases in which OPC-way isn't enough to get data. Then this is we are still evaluating this thing. For example, one of the data we will want to collect are the movement of the robots, and each robot has 7 joints, and for each joint we can read its position, the power consumption of the motor in terms of current, and maybe also the torque, and these values. We need to find the maximum frequency that we can reach. If we reach 100 hertz or maybe 50, we should be almost happy for enough. But I know that are not so higher values. Up to now, the system to conclude, up to now we are not collecting high frequency values with high frequency, but we are collecting statuses and availability of the machine, the current operation, so values that changes maybe once per second or similar. So actually it is not sorry,
it doesn't require too much space on. Okay, thanks.
Maybe the heavier value is the Syslog, since we are using this one not only for the machine but also to log the network firewalls and other system that we have here. And this system logs a lot of data, really. So maybe in this moment the Syslog is the heavier node, and effectively in this slide it is connected directly to the time series. But we are evaluating, and probably will be done in a few days, to move the Syslog before Kafka to, first of all, be able to use the replication of Kafka to unload the data, and also to provide the Syslog to other applications that we could, for example, the analysis of the network rule that the firewalls allows or deny, for example.
Okay, thanks.